I think it's interesting to know that what you said about the supernovas. It's always true that stars, most of them end up in a supernova and collapse, and if they're light enough, they end up as a neutron star. But if they're too heavy, then they have to end up in a black hole. So if there's enough mass, then they are black holes. And so we expect there should be lots of them around, but not close enough to us to see because they're black in itself. But when they grow, and you can see them just because they're so heavy that other things circle them. So the first proper detection, let's say, is not so long ago that people actually traced the stars around the center of our Milky Way, and there was nothing in the middle, but they were all moving as if there's something heavy in the middle.
Yeah.
So that's recent, I think, a few years ago. So we're in the beginning. I'm working on something slightly different from my colleagues here, gravitational waves. Später.
Quick one, just.
Nee, später. So our detectors are not like telescopes, but they are interferometers. So there's a picture of the one in Italy. So these long tunnels through these fields. That is the detector, and what we measure is the change in length. So we work more like a microphone when
changing the wavelength.
No, the change in actual length. So we detect something that squeezes or stretches space-time.
Oh wow! How did you do that?
Yeah, so the only thing that doesn't squeeze and stretch, as everything else, are photons. So if you compare what light sees to what if you put a meter stick, then you don't see it because it shrinks, of course, with space. But if you compare the meter stick to photons next to it, then you see there's something different. So we do exactly that. So we have just laser beams running up and down the tubes, and they should show if space-time changes.
I know what you mean, yeah.
And so these detectors are obviously not like telescopes, so you can't point and say, okay, I'm looking at the moon and then this. So they act more like microphones. So basically we just can hear vibrations in space-time as if a microphone hears vibration in sound. And why we do it is because we believe that everything that's heavy and does something violent, like a supernova explosion or two black holes that meet each other, actually excite vibrations in space-time. So we always have this image, the black hole explosion or the spiraling motion is like if you move something in water, so there are these waves rippling out and we have a microphone somewhere and then pick them up. And the funny thing is we can't actually see them in photons, but we can hear them with these space-time vibrations. So we're not really looking only for black holes, but everything that's heavy, for neutron stars, white dwarfs, and other things. But the black holes are probably one of the main candidates because they're so heavy. So they make strong signals for us. Unfortunately, we haven't seen them yet because our field is new. So we have built detectors and they're running, but they're first versions, let's say. So we call them first generation, and their sensitivity is good enough that if a nearby star would explode, we would see that. But what we need is actually to see half of the Milky Way to actually make good statistics, because nearby nothing explodes right now.
Yeah.
And so we're building new detectors and so on. But we believe that in a few years, 10 years, these detectors will see, like telescopes, a lot of new things in the sky. Among them, black holes.
Wow.
So it's
that's amazing.
Yeah, I mean, and for what black holes actually are, we might be able to do something interesting as well, because there's a theory that describes the black holes. Basically, through the theory, people thought there must be black holes. It's from Einstein, the general relativity, but there are alternative ones as well. Which also have black holes in there, but there are tiny differences, and there are some that believe there are no black holes. And one of the test cases, usually you do test a theory in a lab. You build the experiment, and then somebody says, "Oh, if you press this button, this happens." And the other guy said, "No, if you press this button, that happens," and you just do it, and then you know who's right. We can't do it, but we have some test cases that we hope happen at some point. And the ideal one would be if a tiny black hole falls into big black hole,
Yeah.
and we see what happens. And unfortunately, again, optically you can't see that,
No.
but with a gravitational wave, we could see it. And this type of signal, basically this the how the sound blip really sounds like. This could actually then tell which one of the theories was right. So that's something we hope we can do, but it depends, of course, very much whether we're lucky enough. You need to basically very well set up black hole, so it's there, mostly empty around, and then they could find a black hole and falls in. So we probably have that at some point, but more likely is that there are lots of signals of lots of things falling into the black hole all the time, and we have to wait for a clean signal at some point.
So, how do you know how many there are out there?
Black holes?
Yeah, like there could be some right next to us, and you wouldn't know.
Yes, so no, there could be. So it's very difficult to judge that. So there are lots of different expectations. We all believe now, but most people in astrophysics believe now there is a supermassive black hole at the center of each galaxy.
Is it still a theory though, because you can't see it, so you don't really know?
Yeah, it is still a theory. I mean, there are still some people that believe they can solve the dynamics, that you can see differently, but it's a mainstream theory, so we can't prove it very well yet because, as I said, it's young. So we just got the data recently, and people are working on it, but it looks all very straightforward. So this is the simple explanation that would explain everything. And for the supermassive black holes, I think this has been more or less accepted, even though it's still a theory and we're working on it. What is more difficult to see what happens with smaller black holes. So the supermassive ones are exceptional cases because they have been growing over billions of years, and they're in a special position, and center of galaxy, you can easily point towards and say, okay, let's look whether there is one. But if there are smaller ones around, then it's more difficult to know what they're doing. So there's been a recent paper of people suggesting there should be many hundreds of small black holes in the Milky Way, which we can't yet see because we didn't know where to look, and they have made a theory where we should probably find them. And the theory is that these all come from previous interactions with other galaxies, when our galaxy was still small and young, colliding with others. And the one that's in the center of our galaxy is just the one that stayed and grew, and the other ones were kind of in a larger orbit, so they're kind of orbiting our own massive black hole, but are not staying there. And they have done some calculations how one could possibly look for them. Again, with the same trick that you try to see that stars move in a strange way, as if something heavy is close by. But there are so many stars in the Milky Way, if you don't have an idea where to look, it's difficult. So they made some proposal where to look, and I guess these same people will start looking with telescopes for such patterns. But there's very little information, and we've never seen one. So people claim we can do tiny black holes.
Yeah.
And accelerators, yes.
Yeah, the LHC.
Exactly, and we can have kind of every size.